after spending the morning seeing that everything I've been doing is obsolete, I'm particularly intimidated, but I'll just try to forge ahead. So I'm going to share a bunch of stuff with you, probably too much, but I don't like giving the same talk over and over again. And I have talked about the general things about carbon mineralization for CO2 storage at MIT before. So I kind of threw in a bunch of talks I'm giving, a lot of which is not published, with the result that there's way too many slides. So, so we'll just go along as we can, and hopefully this can be pretty informal. If you start interrupting me, then we're not going to finish. That's fine. And I'm going to stick around afterwards. There's kind of a lunch break for me anyway after the end of the official time, and so if we want to go back and look at more stuff, whatever. And then the other thing to say about this is that it'll go by pretty fast, but I'm fine with sharing all of this PowerPoint with anybody who wants. Okay, so because I'm here, and some people here had 15 minutes of fame saying that we shouldn't bother with carbon capture and storage, I thought I would address that. And then I'll talk about carbon mineralization very briefly, the sort of overall process.
The numbers are the numbers of slides you showed?
Yeah. CO2 removed from air. Well, I think so you add up to that number. And you'll see what you're missing if we don't get to the end, right? Or we can jump around. So, and all these different topics, ending with natural hydrogen production rates and exploration. And I'm a little bit of a hydrogen stimulation skeptic, and probably a lot of you are interested in that. So if I do get to the end, we can talk about that. Okay, but first let's talk about this op-ed in New York Times that came from Charlie Harvey and Kurt House. And they said that clean power from carbon capture and sequestration died with the success of renewable energy. And they claim to be experts on this because they founded some of the first companies that were designed to make money on carbon capture. And they felt that it had been a failure. And then Al Gore, ever helpful, gave a TED Talk in 2023 where he says it's still too expensive. Carbon capture and storage is still too expensive. Direct air capture is also, he says, expensive. And then he gets into the CEO of Occidental has been going around saying that because we bought carbon engineering and we're now removing CO2 from air, this gives us a license to continue operating. And so for a lot of people, the fact that oil companies are interested in it is a bad thing because they've internalized this idea that we don't like oil companies. So anyway, and then today I learned the phrase lame duck. And it inspired me to add this slide depicting a circular firing squad. And I think that, it's really unfortunate given the, I will say, community failure to introduce any kind of greenhouse gas management at scale over the last 30 years. It's really unfortunate that we continue to undermine each other's work rather than accepting the fact that lots of things have to go forward in parallel, and it'll be a long time before we know what succeeds and what fails. So, so not everyone does what Charlie Harvey and Al Gore want in terms of the energy transition. So the point of that op-ed was that we should just get on with replacing fossil fuel energy with renewables and nuclear. Here's the environment minister of India saying India's first task is eradication of poverty. And in essence, our policy is to use more coal and gas, not less. And here is the Prime Minister of India just this year, a proud moment for India, crossing the monumental milestone of 1 billion tons of coal production per year. And so point is, not everyone accepts that burning fossil fuels is a sin. And correspondingly, the energy transition isn't going anywhere near as fast as Charlie Harvey and Kurt House think it should. I like to tell students in New York, we can sit around until we're blue in the face in New York City, talking about what people in the world should do. But for the most part, they don't care what we think and they don't need our help. Okay, so indeed, coal is the main source of electrical energy in India. More than 3/4 of their electricity is produced by coal combustion, and there is some idea that this might go down to about 60% by 2030. And indeed, globally, although coal use for electricity production is declining, it's still 61%. Or 61% of electricity is still is produced by combustion of fossil fuels. And moreover, if we look at projections into the future that aren't made by environmental groups, here's the Energy Information Administration during the Obama administration, and they're predicting that by 2050, roughly half of global electricity generation will still be using fossil fuels. And why do they make this prediction? They certainly didn't think this was necessarily a good outcome, but they know, and I checked, 2/3 of all the coal-fired power plants in the world were built in this century, and the same fraction is roughly true for gas-fired power plants. Those all have an expected lifetime of 40 to 50 years. And so unless you're willing to buy out the investors and shut them down early, we're kind of stuck with that standing stuff. So that's why they make that prediction. It doesn't have anything to do with ideology. Okay, so meanwhile, we're told that in order to, and I had, there are lines on this diagram. We all know there's giant uncertainties and all of these things, but nonetheless, this diagram and others like it serve to provide sort of a starting point for understanding scales of things. So we're told that if we want global warming to remain below 2 degrees C, we should be following this red trajectory in terms of CO2 emissions per year, CO2 and CO2 equivalent emissions per year. And they're saying that if we continue without any abatement, we might follow this yellow curve for a while. I don't really know why they have it going down, but whatever. And so about the green area is abatement by using carbon-free energy and or carbon capture and storage. And because of the legacy issue that I described earlier, I think some significant fraction of that would have to be via carbon capture and storage on fossil fuel power plants. And in addition, down here, in order to, because there are emissions that are very hard to abate, although Ali's going to fix that, but normally we think of a lot of cow burps and stuff like that as very difficult to abate in airplanes and stuff. So there's this stuff that is not green because whoever made this diagram didn't think that there were easy engineering solutions to avoiding those emissions. Therefore, they say that you're going to need 10 to 20 billion tons of so-called negative emission CO2 removal from the air by mid-century and the end of the century. That tends to be expensive because, of course, CO2 in air is less concentrated than CO2 in flue gas. So, for example, if we say this has to be 10 billion tons a year at $100 a ton by mid-century, that's $1 trillion a year. It seems like quite a lot of money. So then we can go back and ask, what is mitigating greenhouse gas emissions worth? And that's a fraught question. I like these figures from the White House Interagency Working Group and then the EPA during the Obama administration. So what they've done, this is so-called social cost of carbon, dollars of damage to the economy or to whatever, to the humans per ton of CO2 added to the atmosphere. And the reason I like it is that it has these probability distributions instead of individual numbers. And it shows the effect of the so-called discount rate. So if you have, I like to think of this as simply the rate of growth of the real economy. There's philosophy papers about the discount rate. Let's not go there. But the real rate of growth of the economy. So if the economy grows very fast and the damages due to greenhouse gas emissions are of a fixed cost, then they become a relatively small proportion of the total economy. If the economy grows very slowly, they're much larger. And so all that. And so I like this diagram because it encapsulates a lot of things that we don't know. But still, everybody looks at it for a while and then says, well, my whole life, the real rate of growth of the economy has been 3%. And so what's the number? And that's $42. And you'll notice the average is displaced from the peak probability because there's a so-called fat tail, right? There's more high values than low. Before, these days is $1.6 trillion in 2007 and $2.4 trillion for inflation. Now, 3% of the global GDP in 2007, 1% of the global GDP now. Okay, so organized and the good thing about the addition that was never was that there were a lot of people there, and they would show. They didn't. I don't have their slides, so nor is this online. So I had to make up their slides, but basically, point is, if I have a process to remove CO2 from flue gas and it's very inefficient, then it costs a lot per ton of CO2 removed. If I insist on removing every nanogram of CO2 from the flue gas, then that becomes very expensive per ton of CO2. And so there's kind of a sweet spot, and $42 a ton is sort of down in here where you maybe get 60% of the CO2 out of the smokestacks. Okay, so at that same meeting, there were a lot of people doing integrated assessment modeling. I like to describe them as Europeans in tight pants, and they were fixated on achieving net zero emissions by the second half of the century. And the coal company, so go back, right? That. And the coal company guys were just like, what are they thinking? Do they have any idea how much that would cost? How could that possibly be practical? So I was sitting in the back, as I like to do, and watching this interaction and trying to figure out how to help the different groups understand each other. And so I took advantage of the fact I had just read the Black Swan Greek book. And I looked at this fat tail of the distribution, and I noticed that finite values are going off the right-hand side of the diagram. And so, you know, there are papers on fat tail distributions of the social cost of carbon. This is not that. This is me fiddling around with Excel in the back of a lecture hall. But I said, okay, so the data on this plot are here, and I'm going to put a fat tail on it. This is now log scale. And there's some finite probability that everyone will die. And there's 10 billion people on the planet when that happens. They're valued at $1 million per person because that's what the average American spends on healthcare in their lifetime. And emissions at that time were 100 billion tons of CO2 equivalent per year. So that gives you a cost of $100,000 per ton of CO2 added to the atmosphere. And if, in turn, if you now recalculate this average because of the power of these kind of fat tail distributions, it's $600 a ton. And I don't think you should believe that. I made it come out that way because at that time, Howard Herzog and other people were saying direct air capture would have to cost at least $600 a ton. So I just made it come out to $600 a ton. And in fact, no one knows the probability of this kind of event. No one even dares to guess. For some reason, you know, the Secretary General of the UN, the President of the United States, previous administration were referring to climate change as an existential threat. Well, what is the actual probability of that existential event? I don't know. I don't think anybody really knows. when we think about existential catastrophic things that might end civilization, we can think about, oftentimes people think about meteorite impacts, and I can't defend it, that you need a bolide about 2 to 10 kilometers in radius to end civilization. And in turn, the probability of those kind of impact events is something like less than 1 ppm per year. And so the risk of catastrophic climate change that I assigned in my spreadsheet is 10,000 times bigger. So maybe we should, if we're going to spend $300 million in fiscal 25 to worry about asteroid impacts, maybe we should spend 10,000 times more, or 2.8 trillion on climate catastrophe. That comes out to $7,000 a ton of CO2. On the other hand, if the probability of catastrophic climate change is similar to the probability of a catastrophic asteroid impact, that works out to less than 1 cent per ton. So do I know where we should be? No, I do not. Okay, so Obama administration, as I said, they came up with a kind of median number for 3% discount rate of $42 a ton. That went up to 51 by the end. And then in came the first Trump administration, and the social cost of carbon went down to $1 to $7 per ton of CO2. And it's kind of remarkable because presumably a lot of the same people in the EPA created this number as well as that number. Not the top administrators, but a lot of the same people. So how did they do that? I'll solicit ideas. What was the rule? What were the changes in the boundary conditions that came up with this very much smaller number?
Economic growth.
They did have a gigantic discount rate, 7%.
It's not enough.
Others?
Eliminating healthcare. Yeah.
No. Okay, so once you hear it, you'll think, oh yeah, of course. They said, we're only interested in damage to the United States. It never occurred to me to ask for the Obama administration damages for global or not, right? And we don't actually live in an isolated cell. We're getting there, but we don't actually live in an island that's independent of the global economy. But anyway, that's what they did. All right, so at $7 a ton, you might as well spend nothing because you won't have any successful abatement. All right, and then in came Biden. First, they took the old Obama number, they reduced the discount rate, and they came up with a number, I don't know what else they did, of $190 per ton of CO2. If you take current CO2 equivalent emissions and multiply it by $190 per ton, that turns out to be about 5% of GDP in 2022. A lot. Okay, so maybe if that's the right number or even close to the right number, maybe we are willing to spend hundreds of dollars a ton on abatement of some of the emissions. So this is, I got this slide from Steve Oldham, who I think was CEO of Carbon Engineering before they sold to Oxy. And the point was, over here, there's easy to abate, cheap solutions, but when we get out here in the 30th to 50th ton of CO2 emissions, it becomes increasingly expensive to abate those emissions. And so at $100 a ton, you can abate about 5 billion tons of additional emissions, and at $250 a ton, according to Steve Oldham, and I think Goldman Sachs, you can abate another 5 billion tons of emissions or so on. So there is an expensive end of the curve that can justify spending quite a bit of money. And now let's just imagine that all greenhouse gas emissions are going to be mitigated or avoided at 50 billion tons of CO2 equivalent a year. And we're going to say the average cost of that mitigation is $200 a ton, which is high. Okay. Is higher than most guesses for the whole banana. Okay, so that's $10 trillion. That's 2% of global GDP in 2050. And if this is a constant real cost in a growing economy, it's 1% of global GDP at the end of the century. So what's our yardstick for that? Oh, okay. So actually, see, it turns out this is a bargain because it's not 5% of GDP. So how do we compare this to something that we care about? So London became the world's largest city in 1821, and there were essentially no sewers. So if you were poor, you threw your poop out the window, and if you were a little bit richer, you had some pipes that led to a cesspool. And they had noticed that cholera outbreaks were occurring in the vicinity of these open cesspools, but they didn't do anything about it. So sort of the dawn of epidemiology, but not action. And then in the summer of 1858, it didn't rain. And in addition to the people, there's also horses. And the streets of London were filling up with poop. And Parliament, the royal court moved out, of course. Parliament was debating whether to move out of the city, and instead they passed legislation. And over the next 10 years, they dug up all the streets in the world's largest city and installed a central sewage system. Cost 2% of GDP for 10 years while they were doing it, and still costs 1% of GDP to deal with municipal solid waste in a city that size. So globally, I think we're spending, I tried to find this number, I think globally we're spending about $2 trillion, or roughly 2% of GDP right now dealing with municipal solid waste. So if we're willing, and the other thing is that doesn't crash the economy, because yeah, you spend that money, but there's also people getting paid to do it. So on that basis, we could probably afford what, so like what I like to say in public lectures is, if you come to think that putting greenhouse gases in the atmosphere is like throwing poop in the street, we've got you covered. And until you think that, we can do research, but we're not really going to do this. Okay, so let's talk about carbon mineralization. I think this audience, for the most part, is pretty familiar with this, but basically the idea that's been around for 30 years now is to combine CO2 with magnesium or calcium-bearing silicate minerals to form solid carbonate minerals, plus in some cases the byproduct will simply be quartz. And the sort of poster child for this is we take CO2 and add it to olivine, which is the main constituent of the Earth's upper mantle, and make magnesium carbonate and quartz. And a couple of points here, this stuff weathers very slowly, even when it's exposed on the surface. It's completely non-toxic. If you insisted on swallowing it, it would probably improve your regularity and it wouldn't hurt you. So, all right, so it's kind of a way of capturing maybe and or storing a lot of CO2. And then not going to leak once you do that. Okay, and then the other piece here to know is that normally the mantle is hidden or separated from the atmosphere in the oceans by the crust, 40 kilometers or so of continental crust and 7 kilometers or so of oceanic crust. But peridotite is really, really far from equilibrium with the atmosphere and the oceans. And sometimes plate tectonics does us the favor of pushing that stuff toward the surface where it's exposed by faulting and erosion. And when that happens, this is like a giant battery. There's this huge spatial gradient in oxygen partial pressure, in water fugacity, and in CO2 fugacity. So this is like a great big source of chemical potential energy. And I have this over here to say magmas that are derived from the mantle are similar, not quite as good, but similar in the sense that they're very far from equilibrium with the surface. And so when they get up there, they have a similar kind of, you can get some reactions for free because they're out of equilibrium with the surface. Okay, and this picture of an outcrop in the Sultanate of Oman kind of embodies all the way. So the black rocks in here are hydrated mantle peridotite, but they contain some olivine still, and they contain very, very reducing iron nickel alloy. They record oxygen partial pressures of something like 10 to the minus 80 bars. And then this red stuff, which clearly is arrayed along these fractures, is pretty close to equilibrium with the atmosphere, so 0.2 bars. So you've got something like 80 bars of oxygen partial pressure gradient across the length of my pencil. And among other things, microbes really like that. Yeah, and then you see these white carbonate veins, which are also forming by reaction between CO2-rich fluids from the surface and these rocks, taking up magnesium and some calcium from the rocks and forming the white carbonate minerals, and the green stuff is hydrated serpentine.
What's the time scale of this?
Well, this particular outcrop a lot of this reaction is on an unconformity that was exposed to the air in the Cretaceous. So, but we can measure this. Let me just go to the next slide. Yeah, so the other thing, what really got me going, because I had been working on rocks in Oman for quite some time, probably the biggest exposure of oceanic upper mantle in the world, pushed up on the Arabian continental margin. So this is an aquifer completely in peridotite, ultramafic peridotite. And what you see here are travertines. So the water table is intersecting with the surface here, and water that's reacted with this peridotite aquifer is coming out on the surface. And this stuff here and here that looks like ice on the surface of these rim pools is calcite. And so the water comes out of the ground, it has no carbon left in it. All the carbon has been stripped by the reactions that I described earlier. There's no carbon left, but it's full of dissolved calcium, which has no home in the subsurface alteration assemblage. So it's pH 12 up to 12 calcium hydroxide water reacting with CO2, pulling CO2 out of the air and making these calcites. They're denser than the water, of course, so when it rains or you throw a stone in these rim pools, the calcite film falls to the bottom of the pool and forms a new layer on these growing calcite travertine deposits. But to answer your question, when you throw a rock in here, or it rains, and you come back the next day, the calcite film has grown back. So for a geologist, this is like the speed of light or something. It's just unbelievably fast. So really knowing that is what got me started, like, oh, well, wait a minute, we could probably do something with this. Okay, so then enough of that. So now we can sort of see that if we have some geologic source of magnesium or calcium or maybe sodium, and we can use it in various ways to capture and or store CO2. And so the first idea people had was, I'm going to mine this rock, I'm going to grind it up, I'm going to ship it halfway around the world, I'm going to put it in a high pressure temperature reactor, I'm going to take CO2 from flue gas, I'm going to combine them in the reactor, and I'm going to make solid carbonate minerals. And you can probably get the impression from the way I'm describing this that that is quite expensive. There are still people working on it, but I think it has remained about $400 a ton since the IPCC first looked at this. Okay, or you can take mine tailings, either existing mine tailings, or you could mine rock for the purpose and remove CO2 from air and or store CO2. And you can also potentially have, rather than bringing the rocks to the atmosphere, you could potentially pump CO2 bearing fluids, either CO2-rich water or supercritical CO2 into the subsurface. And so first, let's talk about carbon dioxide removal from air, otherwise known as direct flow capture. I have no idea why these two terms are not synonymous in people's minds. And first, let's talk about this particular flavor of enhanced weathering. So here's a great big mine tailings pile in Australia. Mount Keith was the world's largest nickel mine. And this top layer here is carbonated. So this has been out for about a year. And during that time, CO2 from the atmosphere has gotten down in here and combined with magnesium from the rocks to cement the tailings fragments with magnesium carbonate minerals. So, and fast uptake in those rocks is mainly by reaction of carbonation of a mineral called brucite, magnesium hydroxide. So if I take just olivine and I hydrate it, I make a mole of brucite and a mole of serpentine, and that assemblage has 17% weight brucite. It's pretty easy to combine this magnesium hydroxide with CO2 to make magnesium carbonate and water. On the other hand, if I have a more silica-rich peridotite and I have this pyroxene mineral as well, I might make no brucite at all. Okay. So it depends a little bit on the lithology. It is true that some serpentine, asbestos, don't use that word in public because we work on these rocks, but some serpentine has a very high surface area. And so some of them, even though the mineral has pretty slow carbonation kinetics, sometimes there's so much surface area that it goes along. So anyway, you can have brucite reacting with CO2 to make magnesite, and also these hydrated magnesium carbonates. So, and I used to have a lecture demonstration where I'd have a little thing from REI with some crushed altered peridotite in it and a CO2 sensor, and you could watch the CO2 go down in that vial in the course of the lecture. Yeah. Okay, and so Greg Dipple at UBC and his colleagues have done a lot of work on this, and they focused on this nickel deposit in central BC. And they went in and they measured the proportion, not only of brucite, but also reactive serpentine, and derived these are all, it's a wonderful thing is there's 80 boreholes at Baptist, and they derived this kind of fence diagram for the amount of so-called labile or reactive magnesium in that deposit. And they get about 2.38% magnesium. When we carbonate the rock, we get about a CO2 to magnesium ratio of about 1. And so you can take up about 2.5 weight percent CO2 in that average tailings there. So let's double that. We think 400 million tons of the right kind of tailings are produced every year at 5 weight percent. Typically in a tailings pile, they're going to add another layer every year. They don't have that much area to work with. So if you cover it, you're done, and you've taken 20 million tons of CO2. So that might be a way to make money, but you know, silly me, I'm an academic, and so 20 million tons is a very small fraction of global emissions, and I have thought that's not such a great idea. Not only that, but anyone will tell you it costs about $10 a ton to mine and grind, quarry and grind average rock. So at 5%, that turns out to be $200 per ton of CO2. So it might seem cheap and robust, but it's actually not that cheap. So, but we could mine the rocks for the purpose. So we have more than 400 million tons of rocks, and we could leave them uncovered for a long time. We could stir them with these little robots and get the CO2 deeper in the pile. We could flow gas through it. And I did this kind of illustrative calculation a while ago where if I wait almost a century, I can bring the price per ton from 185 down to about $90 per ton and take up about 22 weight percent CO2. However, we end up generating absolutely gigantic volumes of tailings. And just for scale, if you're taking 1 billion tons of CO2 via this method, and you're adding 5 weight percent of CO2 per year to those, you end up with 40 meter thick layer of tailings over the area of Washington, D.C. every year. And that might not be a bad idea, but in general. All right, but wait, so here's Mount Keith again, scale bar. And here's their tailings pile. I don't know how thick it is, but 100 meters probably. And so there's a potential for some byproducts. So in igneous ultramafic nickel mines, 50% of the nickel is extracted because it's in sulfides and iron nickel alloy that's dense and magnetic. So it's pretty easy to separate. The rest of it is dissolved at a kind of 2 weight percent concentration, sort of diffusely, uniformly dissolved in the silicates, and that's sitting in the tailings. And so the idea was floated largely by, or sort of championed by Doug Wicks, who was at DOE for a while at RB, that if we could carbonate these tailings and extract nickel and also cobalt at the same time, that would be kind of a value-added process. And so if you can combine those, so the idea is that as you mineralize those tailings, the silicates all dissolve and the cations and anions go somewhere else and reprecipitate. And in the process, the nickel and cobalt that were dissolved in the silicates get to think about where they want to be. And so if you could sort of pull them out in that chain, then you'd have value-added products. And as I'm sure you all know, right now, nickel and cobalt are in high demand because they are desirable, although not essential, products in lithium-ion batteries. And so, if you could pull out that fraction of nickel that was in the rocks that's sitting in the tailings, you could potentially double the nickel production from a given mine. Okay, so we have drilled fully carbonated peridotites sitting above a paleo subduction zone in Oman, and we can look and see when this process happened naturally. These rocks, every single magnesium and calcium atom has combined with CO2 to form carbonate minerals, and the silica is in quartz. So where did the nickel and the cobalt go? We've got lots of core from there, and we can look and see. And what you see, you can ignore all this busy stuff, but what you see is that volatile free, the cobalt and the nickel haven't really moved around very much in the course of that process. They're sort of still in the rock to first order with a typical mantle nickel to cobalt ratio of about 20. So, and we can sort of look at chemical data. I don't have time to explain all the things we've done, but we can see that there's a fair amount of nickel in the carbonate. So that would be easy to extract with acid, but you don't really want to, if we're trying to store CO2, you don't really want the mining company to turn around and dissolve it. And the rest is in kind of nasty looking minerals that won't float and they're not magnetic. Well, they will float, they'll float too much. They won't sink and they're not magnetic. So, but some rocks in very, very highly reduced altered peridotites, you get this mineral. It's really is a mineral. We call it an alloy, but it has a stoichiometry, 3 nickels per iron, awarawhite. And there can be a decent amount of awarawhite. And this is why there's a lot of interest in that Baptiste nickel deposit. They want to use awarawhite as their primary ore mineral. So we had the idea, and these are just equilibrium models, no kinetics. We had the idea that as you carbonate the silicates, you add a big reductant. First we did iron, and that has some pluses and minuses, or just aluminum as a reducing agent. The aluminum doesn't really combine with anything we care about. And all the nickel in an equilibrium model ends up in awarawhite. So, and of course, scrap aluminum doesn't cost very much. So this seems like a cost-effective way to strip the nickel out of the silicate mine tailings and make a very easily extracted nickel and cobalt rich component. And you can even sort of try and design a flow-through process where we're putting the tailings in water and scrap aluminum in the top and CO2, flowing CO2 up through the column. And not only are we potentially extracting all the nickel in awarawhite, but the carbon gets reduced to graphite, which is, if you can get it out, is a valuable product in itself. Okay, so now the other way to solve this volume problem is to recycle your reagents. So rather than piling up the tailings around the capital, we can use the magnesium or the calcium over and over again. And this is really pretty generic. It's not specific to peridotite at all, but you take some magnesium or calcium rich rock, you heat it up, you extract calcium oxide, magnesium oxide, and their hydroxides. You lay them out in the weather. In a few days to a month later, they have, just in the same way that those alkaline springs in Oman do, they have combined with CO2 from the air to make carbonates. Then we stick it back in the furnace. We pull the CO2 off, we store it or sell it, and reuse the calcium and magnesium. And this is the basis for a company called Heirloom Carbon, among others, out in California. And when we first did the techno-economic analysis, we were assuming all kinds of stupid stuff. We were going to use farm machinery to spread the oxide on big fields, and it wasn't very smart, honestly. But we came up as a result, because we were using such simple technology, all existing technology, we came up with a very low cost of CO2 net removed, $75 to $150 per ton at full scale. And because we thought we would like to use oxy-fired methane, so the flue gas is CO2 and water, which are very easy to separate, we could about half the CO2 coming out of this process is generated by the oxy-fired methane combustion, about half of it from the carbonation of these cations. And so if selling CO2 is your goal, the price is even lower. It did require a lot of wind. We were imagining a 10-centimeter thick layer that was very stupid. It still required an area much larger than the King Fahd International Airport, which is the largest thing that humans made on the planet. It's also comparable to this footprint for the carbon engineering process, or the, what's the other one? But anyway, it's not, it seems extreme until you compare it with the others. But since then, Heirloom has gone ahead and thought harder about how to do this and actually hydrate their calcium oxide before they put it out in the weather. And they now get 85% conversion to carbonate in 2.5 days. Now their footprint isn't 165 times faster than what we had proposed in the past because they use very thin layers. But nonetheless, they can get about 8 or 10 times faster than we were thinking. And then they have built this plant in California, where they are doing this commercially, of course, with all kinds of tax credits and stuff, and using renewable power to operate the plant. So their cost, I think now, is somewhere around $200 a ton at full scale, and they don't use methane for fuel, which I thought was a really bad idea, and I still do, but they are unique in this, that they don't use any fossil fuel anywhere in the process. And that's been very helpful in terms of attracting investment, which might otherwise go to Occidental, for example. So they were right and I was wrong. But then to do 1 billion tons of CO2 per year, because this process is now fast, they need about 500 square kilometers. So this is 10 times less than other liquid and solid sorbent methods. And okay, sorry, this is a big elaborate thing saying recent cost estimates still hover around $100 a ton at the low end for full scale. But the area required is 5 times the Denver Earth, just for scale. So 500 square kilometers for 1 billion tons of CO2 removal from air. Okay, I'm not going to run out of reagents. Okay, then we'll quickly breeze through mineralization for storage. We already talked about mineralization on the surface using tailings. And there's all kinds of issues with that we saw. But maybe it's better to bring the CO2 to the rocks underground. The idea we had was to create a permeable network in the rocks, much like you would do for an enhanced geothermal system, and then run CO2-rich fluid through that system, stripping all the carbon out of the water, returning carbon-depleted water to the surface, and you've either just stored carbon or you can use that carbon-depleted effluent to remove CO2 from air. Now, this is obviously being done in basalts, not peridotites, particularly in Iceland. This sort of poster child CarbFix project in Iceland. They are using, they're sparging CO2 through water to strip the CO2 and the hydrogen sulfide, which is also a problem for them, out of the water, and then they inject that CO2-rich, sulfide-rich water into the subsurface where it's mineralized. And then there's a similar project that was done in the Columbia River basalts in eastern Washington state, but instead of using CO2-rich water, they used supercritical CO2. And I don't want to talk too much about this. So what we found, and maybe it's no surprise in retrospect, so this figure is still everywhere on the earth. And it was in this IPCC report on carbon dioxide capture and storage. And they said, okay, when I inject CO2 into an aquifer, first I'm going to require a low permeability caprock to hold it down there. Then as it spreads out, I'm going to have CO2 bubbles in water and pore space. finally, those CO2 bubbles are going to dissolve in the water. And then when your great grandchildren are interested in knowing what happened to it, it will form minerals. And this is all, it turns out this was for a sandstone from the Gulf of Mexico, but it's all over the internet. And when I first gave a talk on what I'm talking about now, some DOE program director was there and he said, well, that was a really great talk, but I'll tell you something, I've never been to fund this. And the reason is this figure. So in fact, you know, we have to change this diagram by an order of magnitude on the horizontal axis. And then we see that, you know, virtually all the CO2 that's injected at Carbfix and Wallula is consumed by carbon mineralization within a year or two. Okay, and the other thing to keep in mind is, particularly for basalt aquifers where the porosity and flow top breccias and some reasonably large horizons, maybe 10 or even 20%, we don't really necessarily, we've always thought of these things in opposition. So you're either storing supercritical CO2 in subsurface pore space or you're storing with mineralization. There's a complete continuum between those. All right, so over the years, what has always worried me, particularly when I got involved with that startup, was the possibility that this isn't going to work at all, because as the CO2-rich fluids spread out, they form carbonate minerals that might fill all the pore space, cover all the reactive surface area, and destroy the aquifer and cause everything to come to a screeching halt. And that we called clogging, and then we had these ideas about reaction-driven tracking coming from long ago. Bill Fife, famous geochemist, said, isn't it interesting that you can say that reactions that fill pore space, like I just did, and thereby, you know, cover a reactive surface area, restrict the flow of fluid, you can say that those are self-limiting, and it's in textbooks, right? Retrograde metamorphism doesn't proceed. So, and he said, well, isn't it interesting then that we all have all these serpentinites, fully hydrated peridotites all over the place? It's the state rock of California, where he was at that time. And so he said, well, maybe there's a feedback. There's a great big volume increase as a result of these hydration and carbonation reactions, right? We're adding mass to the solid from the fluid, and we are reducing the density of the products compared to the reactants. And so both of those things lead to big volume changes. And he said, maybe those volume changes are large enough to break the rock. And then you actually have a positive feedback. All right, so people have looked at this. This is my favorite. This is a University of Oslo group. They're flowing water through brucite from bottom to top. It's a cylinder. It's a synchrotron image of a cylinder of porous brucite. And as that brucite hydrates, there's this big volume expansion, and in turn, that is fracturing the cylinder and consuming all of it. It was a great picture of exactly what we were thinking. And those of you who have ever looked at a partially hydrated peridotite in thin section will see that, wow, this really looks a lot like that. Not that visual similarity proves anything, but.
Quick question.
Yeah.
This doesn't appear to be any confining pressure.
Yeah, it does. And, but they didn't do enough experiments to really tell us exactly what the, but yeah, let's talk about that offline. Send me an email. The thermodynamics of this depend on whether you use the Gibbs free energy or the Helmholtz free energy. All right. So anyway, and then we see these arrays of carbonate veins, very regular. We could discuss that at length, but we won't. Okay, so does this happen? Yes, but we've had a terrible time doing this in the lab. Other than that brucite experiment, there's really not very many realizations of this in the laboratory. Just to show you, so this is something called demolition mortar. You can buy a tub, a lifetime supply on Amazon for about 20 bucks. It's some mixture of calcium oxide and sulfate stuff. And you mix it up with water in a proportion that looks like about a mole of water to, it's all secret, but a mole of water to a mole of calcium oxide. And you have a borehole and you pour the slurry in there, and it's not confined at the top. Okay, and then nothing happens and you go home. Very disappointed. And then you come back after the weekend and the rock has broken. And notice that stuff could have extruded. out the top of the borehole, but it doesn't. It holds on somehow magically. And even after that crack forms, another one forms. So it's clinging to the rock and busting it apart. Okay, and we did some experiments where we put great big piles of weights from a sporting goods store on top of a little tiny piston, on top of cylinders of calcium oxide, and watched them hydrate by introduction of water from underneath. And they could push big weights up, way up. And what's amazing about this is that even while they're doing so, they retain open porosity. I don't think anyone understands this, quite honestly. Okay, but what we do know, people talk about disjoining pressure. I don't have time to go into it, but the idea is that as this crystal grows in this pore, there must still be a supply of nutrients to grow the crystal out here. If I want to push against the pore wall, this part of the crystal has to continue to grow. So there has to be some nanofilm or something. And George Scherer at Princeton, who used to be, or is still probably the expert on all this, said, okay, there's a pressure, maybe only 10 MPa, after which this will close. But we know it doesn't. I've already showed you several examples where it doesn't. The demolition mortar doesn't do that. So I think it must be more complicated. It must be kind of three-dimensional, where there's pillars in that film that hold it open, and then pore space that goes around. Okay, it probably happens in serpentinization. This is kind of the poster child. These complicated looking things are olivine crystals, and they're full of cracks filled with serpentine and iron oxides that have formed during hydration of those olivines with a volume expansion. And in turn, this transparent stuff around is plagioclase feldspar, and it hasn't reacted with the fluid, but it clearly saw the volume changes in these expanding, hydrating olivines and broke. And we can derive, by looking at the crack spacing and thinking about the fracture surface energy, we can derive stresses that were required to produce these crack arrays, and it's on the order of hundreds of MPa. Okay, and then just a typical texture for a partially hydrated peridotite is this. And again, I used to think that first these rocks were pulverized and then the water came in and made the serpentine. But if you look at these, particularly in cross-polarized light, you see there's multiple generations of serpentine. And so it's clear that the cracking and the serpentine growth happened more or less. Doesn't prove that the serpentine broke the rocks, but it might have. And finally, we have not been able to make reactive-driven cracking go with carbonation of stuff in the lab. But this is a picture of an outcrop in Oman. And you see these fragments of serpentinized peridotite that are kind of a jigsaw puzzle. If you took away this white carbonate, they would fit back together. So it's quite clear that the rock fragments moved apart as the carbonate was crystallizing. The rock fragments were not flying in the air. That doesn't prove the carbonate pushed the rock fragments apart, but obviously that expansion happened at the same time that the carbonate. Okay, and then we see fully carbonated rocks, so something can go all the way to completion. But also, I have come to realize we were asking the wrong question. So we don't really care why, we just want to know if this process will clog or continue. And I don't know how many of you, okay, so what I've always thought about is a cylinder forming around this borehole. We're injecting CO2-rich water, and there's going to be a precipitation front out here somewhere where carbonate starts to precipitate and clog everything up. That's the picture that's been worrying me for 20 years. 20 years. And right, and so we'll ask in a little while whether that's a good picture. But for now, where would that be? And so this is the kind of thing, I don't know how many of you are familiar with this kind of plot. And if you're not, just relax and go with the flow. But so here we're looking at water rock ratio. These are equilibrium models. We're reacting CO2 bearing fluid to 50 bars and 50 degrees C and around a borehole. And you can either think of this scale here as distance, where at any given time, the farther I am from the borehole, the lower the water rock ratio. Or you can think about this as reaction progress. If I'm sitting in one place and injection is continuing, then the water rock ratio in that place is going to gradually go up. So this is fine. And the scary thing about this kind of model is that this is predicting a 60% solid volume increase in rocks that only have a few percent porosity. And basalts are better, but still reacting with kind of a generic basalt, same other conditions, 30% solid volume increase in rocks that rarely have more than 10% porosity. So this is what's been worrying me all these years. Now, we also discovered along the way that if we alter the rock beforehand, if we already have hydrated the rock, so now this is a serpentine rock made from this igneous dunite, then the volume increase is less, but it's still big. So the first takeaway is we've always been desperately looking for fresh olivine and reacts really well with highly altered rocks that might actually be better. So then the other thing I want to do is convert this water rock ratio to distance at a given time. And three-dimensional reactive flow models that you can buy or rent from the national labs and what have you sort of do this, but they do this in a sort of 40 parameter way, and it's a little bit hard to keep track of what's really going on. I could stop. All right.
There's an excursion, some people.
No, I know, and that's fine, but I don't want to keep people here beyond there. Anytime you want to leave, go. Okay, so I just wanted to do some algebra instead of these complicated models. And so, you can think about a radial geometry, and there's a zone in here where you're going to start precipitating minerals and so on, and you can do a bunch of algebra. And this isn't really totally finished, to be honest with you, but you derive a relationship in which the radius of any place is equal to a bunch of constants times time divided by the water rock ratio, or conversely, the water rock ratio is equal to these constants times time divided by the radius at some time. And then you can figure out, you can take that complicated geochemical model and turn, well, first of all, water rock ratio versus radius is varying with time. And the longer you pump, the bigger the radius, right? For a given water rock ratio. Now we can look at solid volume change or porosity filling as a function of the radius and time. And you see that these numbers are really, really high. And at early times, they're high, very close to the borehole. And actually, that makes sense. So initially, when I'm putting this carbonate-rich water into a rock that's reacting really fast, but well, this is an equilibrium model, reacting instantaneously, of course, I fill all the pore space right around the borehole. So I've now demonstrated that carbfix can't work. And yet, it has been for years. So yeah, but that's what I just said. So the solid volume increase is really high at early times near the borehole, and even at large times in radii, you get big amounts of precipitation in the pore space. So the answer, at least some of the answer to why carbfix works is very simple. It's kinetics. So the instantaneous equilibrium there gives us this big burst of crystallization right around the borehole. But imagine if the reaction, the carbonation reaction, was infinitely slow. Then the carbon concentration in the fluid would never decline, and the carbon concentration in the rock would never go up. So infinitely slow kinetics, I can go on forever pumping this fluid into the reservoir. So we can stick kinetics into this simple geometric model, and I really don't know why I bothered to show all this algebra, because there's nowhere near enough time to explain. But it's pretty simple. Then you pick a kinetic model. And then you find that, of course, right, that I can get the carbon a lot farther away from the borehole at any given time before I crystallize a lot of carbonate. And so we, at the radii for a given water rock ratio, go way up. And the amount of crystallization in the pore space goes down to a few percent or less, and is almost time independent.
Do you assume precipitation occurs at saturation under equilibrium?
Yes.
Yeah.
I mean, I'm basically, it's kind of a weird model because it's a bunch of very simple algebra and then these very complicated realizations that tell me about the body. Okay, so the second takeaway is we've been looking around for things that go really fast, but actually there is such a thing as too fast. And kinetics are actually helping us get more carbon further out into the reservoir, and maybe it will never clog up at all. And also, maybe this is the wrong picture. And I hope some of you in here are modelers, because what I want to explore now is this reactive infiltration instability. So when I was a graduate student, I was very fascinated with this, where if I'm flowing a solvent through a partially soluble porous medium, let's say I start out with a planar reaction front, any perturbation in anything, the permeability, the porosity, the reactive solid phase distribution, any perturbation will cause, in some conditions, dissolution channels to form along the primary vector of fluid flow and starve the surroundings of flow. And so you get exponentially growing dissolution channels with high porosity. And so now, okay, we're pumping this solvent, carbonic acid, into the formation, and we should turn this thing sideways and think about channeling in the reservoir. And in fact, some of you may know, there was a lot of interest in acid flooding. There may still be acid flooding in the oil industry for enhanced oil recovery. And back in the day, Dacord and Lenormand were working with Schlumberger, and they did these experiments, and they had acid flowing into plaster out of a borehole, and then they would cast the resulting dissolution channel network with Wood's metal, and they could then dissolve away the plaster and image the porosity before CAT scan. And they made these nice networks, and they was fractal. That was the fractal years, so they said they were fractal. But anyway, they're interesting for sure. And now this is my favorite paper on the reactive infiltration instability, and it's done by some petroleum engineers. And I just want to quickly walk you through it. So, you know, there's all kinds of fancy stuff to do with dam color and Peckley numbers in here, but just imagine that we're going to hold everything constant except the velocity of the fluid flow through this porous medium. This is a model. They also did realized experiments. So if the flow is very slow, then lateral concentration gradients in the fluid get smoothed out on the time scale of the fluid flow, and this dissolution channel will just migrate upwards as a plane. If the flow is really fast, then every pore turns into a channel, and there's no organization at all. And then there are these intermediate flow rates where the reaction infiltration instability is manifest in the formation of these elongate dissolution channels. So the point is that you can tune the reaction infiltration instability. So now this is maybe pretty obvious to you guys, but we did a whole bunch of models back in the day where we made dissolution channels, but they're not hard enough, working with Dan Rothman and others. Also did experiments where we had, initially, we fed in this very highly structured channel network, these sort of Hieronymus Bosch arms in here. And we had, instead, in order to maintain equilibrium with the solid, the fluid had to precipitate. And what happens very rapidly is the fluid flow diverges, becomes very diffuse, and destroys all that organized porosity network. And now these people, Budek and I can't pronounce that, you probably can, Zuzak, in Poland, sort of, but also at the University of Minnesota, have been doing these kind of models where they combine the reaction infiltration instability in making dissolution channels with precipitation. So as the fluid reacts with the solid, it flips from dissolving to precipitating stuff. And they're beginning to get to the place where we need to be in terms of understanding what actually happens in 3 dimensions around this pore. It certainly doesn't look like a planar precipitation. Okay, and finally, if you could tune this is an idea. We actually have a patent that might have this in it, but we're imagining, forget about the reactive rock. Let's imagine this is a sandstone we're gonna put carbonic acid in one side and calcium hydroxide in the other side. We have to give the fluid a place to get out, and so it gets out. And so, of course, we're gonna make calcite in there somewhere. And in this very simple model, we've made a wall of calcite, destroyed the aquifer, no more to do. But now I could turn up the flow rate of the acid and reduce the flow rate of the base and make a hole in the wall. And then I can do it again, and you could actually sort of optimize the storage capacity of that pore space for carbon. Or there might be lots of other things to do with this. All right, now I'm out of time and more than then so. So I can either talk about natural hydrogen or I can stop.
Keep talking. Talk about it.
Talk. Okay, cool.
Quick question. Firstly, you're
Yeah.
spending a lot of time talking about injection of CO2 dissolved in water.
Yes.
But what are your thoughts on supercritical CO2 injection, where you're relying on the water in situ to dissolve the CO2 and drive some of the reactions? So you'll have some kind of different reaction front
Well,
happening.
the pH, so I have a hard time thinking of the pH of a truly pure supercritical CO2 fluid, but as soon as it reacts with a mica or does anything, it's going to be an aqueous CO2 solution. And then the pH is 3. And so a lot of what I've been saying is different, but the mass balance changes a lot. So I'm able to get more carbon to a given place sooner. And indeed, one of the things that we still haven't done in the lab is to try to do reaction-driven cracking with supercritical CO2.
Thanks.
All right, so, and we could, but we just haven't. So a big change, except these rocks are still peridotites. And they're still reacting with surface waters. And this particular thing is a pool with magnesium carbonate precipitation on the bottom of it. And in that pool, there are little bubbles of gas. And this is a slightly different pool, but here is a movie where you can see this little fish swimming around, and then every now and then this little crater emits a stream of gas bubbles. And it's been known for a long time. It's been known for a long time that in a lot of these places, that gas is dominantly composed of hydrogen. We went out there to measure those fluxes, which hadn't been done, and we took this little tiny accumulation chamber with a cheap industrial hydrogen sensor, and it would take like 15 seconds over one of those bubble sites, and then 1,000 ppm would be reached, and the sensor alarm would go off, and we couldn't get a time series, so we ended up using this garbage can as an accumulation chamber, and then we could get a decent time series and make a flux measure. And so there's a bunch of different places in Oman where this is happening, and we went to a lot of them. And so we get fluxes that converted into numbers that are finite, about 10,000 moles of methane and about 100,000 moles of hydrogen per year from some of these springs. Okay, and so one thing that's a little bit uncertain is where does that hydrogen gas actually separate from the water that it's in? And so, as you probably all know, the solubility of hydrogen in water is pressure dependent. In this pressure range, it's almost linear. There's a little bit of a temperature dependence, but not much. And then the salinity matters a little bit. We won't worry about that. So the question is, when we see those gas bubbles coming out, is it because we have a dissolved hydrogen-bearing fluid at depth that's rising and then degassing at a shallow depth, or is it actually producing hydrogen at a deep depth? And we don't really know, but it's worth raising that point because some people, including Doug Wicks at DOE, assumed it was this. Okay, so then in the rocks, first of all, when we look at drill core, we see this shallow oxidized horizon where almost all the iron is ferric. We see this intermediate horizon, which is black, and I'm not going to go into this too much, but it's black because of microscopic and submicroscopic sulfide. And then we see the deep area is green, and most of the iron in there is still ferrous. And in those rocks, we see all kinds of ridiculous minerals you've never heard of: hazelwoodite and awaroite. Remember awaroite, the nickel iron alloy, made of copper, all sorts of things that are indicative of very, very low oxygen partial pressure. And we can do models of those. And so here's oxygen partial pressure on the horizontal axis, 10 to the minus 80, 85 bars, and sulfur fugacity on the vertical axis. And mineral assemblages that we see are all consistent with a oxygen partial pressure of something like 10 to the minus 85 bars when the confining pressure is 50 bars, and I forget what the temperature is here, but some temperature appropriate for that depth. And so that happens to be right at the place where water breaks down to form hydrogen. So we do see records in the rocks that the oxygen partial pressure did get down to the point where you could form hydrogen in situ at those depths. And indeed, when we look at water in the boreholes that we made for various reasons, the black line, okay, so this is a complicated diagram. This is pH in blue. This is partial pressure of oxygen in red. This is depth in verticalness. And the black lines are for the different, given pressure temperature conditions in those borehole waters, are the place where oxygen or where water would break down to form hydrogen. And so in some boreholes, the water seems to be pinned right on that hydrogen formation reaction. So what's happening is that the ferrous iron in the rocks is reacting with water to form ferric iron and various minerals and hydrogen. And initially that's dissolved hydrogen, but eventually you get to the point where the fluid is saturated in hydrogen gas. 1.5 to 7.5, because of the stoichiometry of this reaction, 1.5 to 7.5 kilograms of peridotite have to be oxidized to produce a mole of hydrogen. And so that works out to a peridotite to hydrogen weight ratio for rocks with 10 weight% iron, mostly ferrous. That works out to a weight ratio of 3/4 to 3 tons of rock per hydrogen, per ton of hydrogen. So, sorry, per kilogram. So 700, I'm too fancy. So 750 to 3,250 kilograms of peridotite per kilogram of hydrogen. Okay, and then we used an intermediate value to look at the gas fluxes and say how many kilograms of rock had to react to give us that gas. Okay, so we have these different springs, and these are the cubic meters of rock that have to react per year to give us the amount of hydrogen that we observe coming in. And then it gets and then we can do a similar thing for the methane. But then it gets complicated because we don't really know the size of the source region. But we said, okay, well, we can take the catchment size as kind of an upper bound, and we're going to make it. I forget, but anyway, we chose some parameters for the width and depth, and we assume that there's some fast path that's taking this hydrogen-rich water and bringing it to the surface. So we're taking a fairly large rock volume, making hydrogen, and extracting that at a localized spot. Okay, oh, there we go. So there's the catchment volume that we looked at and the mass of those catchments. And so using the smallest volume of the catchment yields the fastest generation rate of hydrogen per kilogram of rock. And that ends up to be about 10 to the minus 13 weight ratio, 10 to the minus 13 per second. And if the catchment that's reacting is larger, then those numbers proportionally go down. Okay, so maybe microbes are eating up the hydrogen. And maybe there's a lot more hydrogen being formed down there, but the microbes are munching it up. But whenever I was giving this talk, Alexis Templeton would kick my legs out from under me and say, what about the microbes? So, all right, what about the microbes, Alexis? So meanwhile, we see quite independently in the course of the Oman drilling project, we sampled a lot of mutually cross-cutting serpentine veins and carbonates, and we could then do carbon-14 analyses on the carbonates. And it's very, very approximate. We derive an estimate of the rate of serpentinization of about 1% per 10,000 years, which comes out to about 3 × 10⁻⁴ per second. And so again, on this plot with 4 orders of magnitude on the vertical axis, that's roughly consistent with the fast end of the iron oxidation rates that we derive from the hydrogen process. But what about the microbes? Oh, we haven't quite got there. Okay, I don't really want to do. You can make stories about laboratory measured rates that make this all okay. Okay, so right, so you have 10 weight % iron in the peridotite. That a gram of iron oxidation makes 0.014 grams of hydrogen. We have, let's suppose we access a cubic kilometer of rock, 3 × 10⁹ 3 gigatons of rock. We know the rate of formation, and we end up saying you can make the natural rate, if you could extract it, 4 tons of hydrogen per cubic kilometer of rock per year. So at $2 per kilogram, that's only $8,000 per cubic kilometer of rock per year. And we think that, given probable costs of drilling and so on, that this rate would have to be increased by a factor of about 10,000 to make a profit. Okay, what about the microbes? So when we go away from springs, we can't measure fluxes that are different from 0. So as far as we know, to the extent that our detection limits allow us, we can use methane. We're much more sensitive in measuring methane, and then likely methane to hydrogen ratios to nail down our detection limit, to drive it down quite a bit, but we can't detect any diffuse degassing away from those springs. And so what about the microbes? So we know the cell density in the drill core from Oman drilling. And so we know how much carbon is in those little organisms. And we can infer that the cells are replaced once a year, and it costs a joule per second per kilogram of carbon. And then we can figure out, given the cell density and their replacement rate and the energetic requirements, we end up saying that they are consuming about 95 billion joules per cubic kilometer per year. And then we can look at the enthalpy of the methane forming rate. What these guys are, these are methanogens. They're eating hydrogen in the shallow part of the aquifer where there's some CO2 around. They're eating hydrogen and CO2 to form methane and water. We know the energetics of that reaction. And so we can figure out how much they're eating. And by God, it is 4 tons of hydrogen per cubic kilometer of rock per year. So they're eating exactly what we calculated that is forming. And well, that actually, in retrospect, this took us a long time to do this, but in retrospect, it's obvious. There's as many microbes as there is hydrogen to eat, and no more and no less. And if you made more hydrogen, there'd be more microbes. So, and Alexis has a neat idea, which I hope I won't be sued, but if you drill below these methanogens and extract, and also there's permeability gradients in here, and extract your hydrogen below the methanogens, you could probably bypass them. Okay, there's a bunch of words on here, but if you want to have the PDF or whatever, I'll give it to you. The bottom line is we need to go about 25,000 or 10,000 times faster to make a profit. And we can do this on the back of an envelope, as we did in one paper, or Alexis Templeton and a group of us did a much more complicated kind of techno-economic analysis of this. But here's the rates that we measured in Oman, and then sort of 100 squared or 10,000-fold acceleration by either increasing the temperature or increasing the reactive surface area, or a combination of both of those. Now, I don't think, it's not, I don't, increasing the temperature in a big rock volume is somewhere in the neighborhood if possible, but you know, you could imagine maybe, and there's certainly lots of startups out there that want to persuade you that they could increase the reactive surface area by a factor of 10,000. I personally am not going to invest in this. And then we see, you know, like as in Oman here, where's Oman? Here, but we do see places where the hydrogen flux tons per year is quite a bit higher. This place in the Philippines, a nice paper by Aquino et al. This year, this place in Albania in a paper last year. But these guys attribute these fluxes again to accumulation of hydrogen in the reservoir and then relatively recent tapping of that reservoir. And there's reasons. Like you can look at these places in the Philippines and you can figure out they would use up all the peridotite in the entire Tabalis ophiolite in much less than the age of the ophiolite if this is what was going on. Okay, so that's what that says. All right, but on the other hand, if we have a reservoir that's tight to hydrogen, and it's amazing, but it is also clear from places like in Mali that there are such reservoirs, then you can, if you have this kind of accumulation generation rate that you accumulate over 10 million years, you can end up with 4 billion tons of hydrogen in a 100 cubic kilometer aquifer, and that's worth $8 trillion. And where would I look? So the thing about having a permeability barrier is we've got to get water in to do the iron oxidation. So if I have a permeability barrier, how am I going to get the water in? So my favorite spot to look is above subduction zones where the mantle wedge is undergoing hydration. And presumably hydrogen is migrating upwards, and then there's sediments sitting on top that could form a trap. And just to give you, there's a pretty decent amount of data from the Izu arc, 4-arc area, because we have boreholes and seismic studies. And the interesting thing about this is that these potential cap rocks circled in red here, nano oozes and clays and stuff, are sitting above high porosity potential reservoir rock. And all that is only a couple, 3-4 kilometers below the sea. So that's accessible via drilling. It's interesting seismic target. And it makes sense to me that, you know, the food is coming in the bottom here, which is otherwise kind of an unusual scenario in the Earth. But we've got cap rocks on top to trap the products. And that's all I've got.
Questions? Tony.